Today we are going to discuss stereochemical aspects of nucleophilic substitution reaction. In order to understand the stereochemical aspect of substitution reaction, we need to learn some basic stereochemical principles and notations like optical activity, chirality, retention, inversion and racemization. First is optical activity. The plane of plain polarized light produced by passing ordinary light through Nicol prism is rotated when it is passed through a solution of certain compound. Such compounds are called optically active compounds. First of all, try to understand what is the plain polarized light. So I will draw here. So if I can show, this is the normal light, which is polarized in all the direction. So here, when the normal light, this is the normal light which polarized in all the direction. When this normal light passes through a Nicol prism. So here, this is the Nicol prism. When this normal light passes through a Nicol prism, you will get plain polarized light, which is polarized only in one direction. So here you will get this light. As this light polarized in only one direction, this is called plain polarized light, or in short I can call it PPL. So plain polarized light, I can write it short as PPL. So when this plain polarized light passes through optically active compound, so here optically active molecule or compound, it rotates plain polarized light either in right direction or in the left direction. So this was the previous, I can draw the dotted line to show the previous rotation of light. And if it rotates the light to the right direction, so when it rotates light to the right direction, or the other option, it may rotate the light in the left direction. So this was the previous rotation of light. And if we rotate the light in the left direction, so here it rotates the light in the left direction, and here it rotates the light in the right direction. So here, read from the book. The angle by which plain polarized light is rotated is measured by an instrument called polarimeter. If the compound rotates the plain polarized light to the right or clockwise direction, it is called dextrorotatory, the Greek word for the right rotation, or the D sign. And it is indicated by placing positive sign before the degree of rotation. So when it rotates light in the right direction, they are called dextrorotatory, or the angle by which it rotates the light. For example, this angle is theta angle. Here I will represent the rotation of light by writing plus before theta. So this is the dextrorotatory compound. Such compounds are called dextrorotatory. When it rotates the light in the left direction, I will place negative sign before the angle of or degree of rotation. So here I will write negative theta. So this is the levorotatory. Now let's read from the book. If the light is rotated towards left or the anti-clockwise direction, the compound is said to be levorotatory, or the L form or the negative sign is placed before the degree of rotation. Such plus or minus isomers of the compound are called optical isomers, and the phenomena is termed optical isomerism. Such isomers are called optical isomers. Optical isomers, they exist as D form and L form, plus or minus. Now let's read the molecular symmetry, chirality and enantiomers. The observation of Louis Pasteur that the crystals of certain compounds exist in the form of mirror images led to the formulation of modern stereochemistry. He demonstrated that the aqueous solution of both types of crystal shows optical rotation equal in magnitude but opposite in direction. He believed that this difference in the optical activity was associated with a three-dimensional arrangement of atoms in the molecules called configurations. The two types of crystals. Dutch scientist J. Van Hoff and the French scientist C. Lee Bell, in the same year 1874, independently argued that the spatial arrangement of 4 groups around the central carbon is tetrahedral, and if all the substituents attached to that carbon are different, the mirror images of the molecule is not superimposed on the molecule. Such carbons are called asymmetric carbon or stereocentric. The resulting molecule would lack symmetry and is referred to as asymmetric molecule. The symmetry of the molecule along with non-superimposability of mirror image is responsible for the optical activity in such organic compound. We know carbon has 4 valency, so they are tetravalent, and tetravalent carbon has tetrahedral geometry. Now let's draw tetrahedral structure in the 2D. So this is the carbon and there are 2 in-plane bonds. These are the 2 in-plane bonds. This bond is the front bond and this is the rear bond. So that's how we can draw 4 valencies of tetrahedral carbon in 2D plane. If these 4 valencies are bonded to different groups, for example, this is A, B, C and D. Such carbon which is bonded to 4 different groups are called asymmetric carbon. So this is the asymmetric carbon which is bonded to 4 different groups. So there are 4 different groups bonded to carbon. This carbon is called asymmetric carbon or stereocentric, and such molecules are called asymmetric molecules. Mirror image of such asymmetric molecules are non-superimposable on the molecule. So let's draw another structure and place a mirror in front of this molecule. So here I will draw the structure of the above molecule. So this is front bond and this is rear bond. It is bonded to D, here it is bonded to C, this is B and this is A. Now if I place a mirror in front of this molecule, you will get the mirror image of this molecule. So this is C. I will see B at this position and A on this position. This rear bond will appear as front bond and the front bond will appear as the rear bond. This will be attached to C and here it will attach to D. When I try to overlap the image of the molecule over the molecule, so here when I try to place over it, you can easily see C overlap with D and D overlap with C. So this molecule, the mirror image and this mirror image is not superimposable on the molecule. So here, what is written here? The mirror image of the molecule is not superimposed on the molecule. Such molecules are called asymmetric molecules. So this molecule is asymmetric molecule as its image is not superimposable on the molecule. And another way to find out the asymmetric molecule to identify the carbon, if the carbon is bonded to 4 different groups, then the molecule will be asymmetric and the carbon will be asymmetric carbon. Now let's read from the book. The symmetry and asymmetry are also observed in many day-to-day objects. Sphere, cube, a cone and all the identical to their mirror images can be superimposed. However, many objects are non-superimposable on their mirror images. For example, your left hand and right hand look similar, but if you put your left hand on your right hand by moving them in the same plane, they do not coincide. The objects which are non-superimposable on their mirror images, like a pair of hands, are said to be chiral, and the property is known as chirality. So another name, asymmetric molecules are also called as chiral molecules. Chiral molecules are optically active molecules. So here, chiral molecules are optically active, while the objects which are superimposable on their images are called achiral. These molecules are optically inactive. So now we know chiral molecules are optically active. The above test of molecular chirality can be applied to organic molecules by constructing model and its mirror image by drawing three-dimensional structure and attempting to superimpose them in your mind. There are other sites, however, that can assist us in recognizing the chiral molecule. One such aid is the presence of single asymmetric carbon. Let us consider two examples of molecule propane-2-ol and butane-2-ol and their mirror images. So here they have drawn the structure of propane-2-ol. And then they place a mirror in front of propane-2-ol. When you see the image, here OH is on the right side of the carbon and in the mirror image, it is on the left side of the carbon. And again, when you rotate this image at 180 degrees, you will get the same molecule. This A and C are identical to each other. So you can see very clearly propane-2-ol does not contain any asymmetric carbon, as all the four groups attached to the tetrahedral carbon are not different. CH3, CH3, there are two identical groups. Due to the presence of these two identical groups, this molecule is achiral. We rotate the mirror image B of the molecule by 180 and try to overlap the structure C with the structure A. These structures completely overlap, thus propane-2-ol is an achiral molecule. Now, here, the structure of butane-2-ol. When you place a mirror in front of it, OH which is bonded to right side in the mirror, it appears on the left side. Here this is CH3, C2H5. Again, rotate the molecule at 180 degree, you will get the structure F. When you try to overlap this structure F on structure D, these two are non-superimposable. And here also you can simply see this carbon is bonded to OH, H, CH3 and C2H5. All the four groups are different. So the carbon is chiral carbon and the molecule will be chiral molecule. Such common examples of chiral molecules such as 2-chlorobutane, 2,3-dihydroxypropanol, bromochloroiodomethane and 2-bromopropionic acid, etc. You just have to identify whether the carbon to which four groups are bonded are different or not. If all the groups are different, the molecule will be chiral. The stereoisomer related to each other as non-superimposable mirror images are called enantiomers. So here the structure B, structure D and F, they are enantiomers. Enantiomers possess identical physical property like melting point, boiling point, refractive index, etc. They only differ with respect to the rotation of plane polarized light. Means they are differ only in the optical activity. If one enantiomer is dextrorotatory, the other will definitely be the levorotatory. However, the sign of optical rotation is not necessarily related to the absolute configuration of the molecule. That means, just on looking at the configuration of the molecule, you cannot predict whether the molecule will be dextrorotatory or the levorotatory. You can only come to know when you place the molecule in front of plane polarized light. By the polarimeter, you will be able to know whether the molecule is dextrorotatory or the levorotatory. A mixture containing two enantiomers in equal proportion will have zero optical rotation. As we have learned earlier, if the one isomer rotates light in the right direction and the other isomer rotates the light in left direction, the rotation of light will be same, only direction will be different. For example, one will rotate light at 60 degree right and other will rotate light in the 60 degree left. So when you take both the molecules in equal amount, one will rotate light in right and the other will rotate it in back. So the resulted rotation will be 0. So here it is written, the rotation due to the one isomer will be cancelled by the rotation due to the other isomer. Such mixture is known as racemic mixture or racemic modification. The racemic mixture is represented by prefixing Bl or plus minus before the name. For example, plus minus butane 2-ol. The process of conversion of enantiomer into racemic mixture is known as racemization. Now let's try to solve example 6.8. Identify chiral and achiral molecule in each of the following pair of the molecule. In the first pair, so let's observe in the first pair, this is the carbon and it is bonded to H, CH3, Br and OH. So all the four groups are different. So this molecule is chiral molecule. So this will be chiral. While in the second structure there are two bromine bonded to the same carbon. So this carbon will be achiral and the molecule will be a chiral molecule. In the second set of molecule, here this is the carbon to which four different groups are bonded. Here this is one big group, this is methyl, this is OH and this is H. So this carbon is bonded to four different groups. So this the first structure will be chiral molecule. Here in the second, these two groups are identical to each other. So this molecule is not chiral. So this molecule will be a chiral molecule. In this structure, this carbon is one side it is bonded to Br, other side it is bonded to methyl. Here it is bonded to ethyl and the fourth side it is bonded to hydrogen. So this carbon is chiral carbon and the molecule will be chiral molecule. While in the second structure, this carbon is bonded to two hydrogens. That means it is a chiral molecule. Now come to retention. Retention of configuration is the preservation of spatial arrangement of bonds to an asymmetric center during the chemical reaction or transformation. In general, if during a reaction no bond to the stereo center is broken, means the carbon to which all four bonds are different, do not involve in the chemical reaction. Then there will be no change in the stereo center of the molecule. The product will have the same general configuration of the groups around the stereo center, that of the reactant. Such a reaction is said to proceed with the retention of configuration. Consider as an example, the reaction takes place when minus 2-methylbutane 1-ol, that means the liborotatory molecule, is heated with concentrated hydrochloric acid. Here this is the structure of 2-methyl-1-butane. Reaction takes place at this carbon and this carbon is not a stereo center or the chiral carbon. Chiral carbon is present next to it. This is the stereo center carbon. As the reaction takes place next to the stereo center, so the configuration of stereo center will remain same. So here you can see the configuration of this part of the molecule is same as before. So that's why such reactions takes place by retention of the configuration. It is important to note that the configuration at a symmetric center of reactant and product is same, but the sign of optical rotation has changed in the product. This is so because two different compounds with the same configuration at asymmetric center may have different optical rotation. One may be dextrorotatory, while other may be levorotatory. The inversion, retention and racemization. There are three outcomes for a reaction. Reaction at asymmetric carbon atom. When bond directly linked to asymmetric carbon is broken, consider the replacement of groups X by Y in the following reaction. Here this is the reactant molecule. When this X gets replaced by Y, if A is the only compound obtained, the process is called retention of configuration. Note that the configuration has been rotated in A. Here you need to learn how to assign the configuration. You can find the link of video in the description box to assign the configuration of the molecule. But quickly I will try to explain it here. For example, this is carbon and here this is the front bond, here this is rear bond and these two are in plane mode. For example, this is bonded to CH3, here it is bonded to Br, here it is bonded to C2H5 and here it is bonded to hydrogen. Now arrange these molecules in the decreasing order of their molecular mass. So bromine will get first, hydrogen obviously comes at last because the atomic mass of hydrogen is least. Then C2H5 comes at second position and CH3 comes at third position. Now draw an imaginary arrow from first priority to second priority. So here I will draw an imaginary arrow from first to second priority. As I have drawn this imaginary arrow in the left direction, the configuration of molecule will be S. Now in the another structure, if I draw another structure, here this is carbon and this is bonded to CH3. Here it is hydrogen and there are two other groups. One is bonded to Br and other one is bonded to C2H5. Now again assign the numbers to different groups. So Br will get first number, hydrogen will get fourth number, C2H5 will get second number and CH3 will get third number. Now again draw an imaginary arrow from first to second. So here you will get the arrow in the right direction. So the configuration of this molecule will be R. And the configuration of this molecule is S. So that's how you will get different configuration by the different position of the groups attached to chiral carbon. So here as X and Y are not defined here, we cannot assign the configuration of the molecule. So that's why you will get difficulty to find the configuration of the molecule. But if the reactant and product, they both have the same configuration. So reactant and product have the same configuration. Means reaction takes place by the retention of configuration. Retention of configuration. If they have opposite configuration, means the reaction takes place by the inversion of configuration. If they both have different configuration. So if reactant and product, they both have same configuration, reaction will take place by the retention of configuration. If they have different configuration, reaction will take place by the inversion of configuration, means R become S or S become R. While in case of retention, S will remain S and R will remain R. So in case of retention, if the configuration of reactant is R, in case of product, it will remain R configuration. While in case of inversion of configuration, if the reactant configuration is R, while changing in the product, the configuration changes to S. So that's why it is called the inversion of configuration. As it is written here, if B is the only compound obtained, the process is called inversion of configuration. The configuration has been inverted in B. If 50-50, if you get both the mixtures, if you get reactant configuration is R, but in the product you will get R as well as S. 50% R and 50% S. Then you will get the racemic mixture. If 50-50 mixture of A and B are obtained, the process is called racemization and the product is optically inactive. as one isomer will rotate the plane polarized light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanism by taking examples of optically active alkyl halides. In case of optically active alkyl halide, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attacks itself on the side opposite to the one where halogen atom is present. So why do you get inverted configuration for SN2? Because nucleophile attaches itself on the side opposite to the one where halogen is present. When -2 bromo-octane is allowed to react with sodium hydroxide. So this is -2 bromo-octane. So this carbon is the secondary carbon. So this alkyl halide is secondary alkyl halide. When this OH negative ion nucleophile will attack from back side of the molecule and expel the Br in the form of Br negative. Br is attached right side of the molecule and in the product OH will get attached on the left side of the molecule. Now if you try to assign the configuration of this given structure. So let's draw the structure. Here this is carbon and these two are in plane bond. This one is the rear bond and this is the front bond. Here it is attached to CH3, here hydrogen, here C6H13 and here it is bonded to Br. When OH negative ion attack from the back side of the molecule, you will get carbon. So here OH will get attached on this side. This is the front bond C6H13. Here this is hydrogen and here it is bonded to CH3. Now assign the configuration of both the molecules. Now assign the numbers to these groups. So Br has highest atomic number, so it will get first priority. Hydrogen will get fourth priority. Here the carbon is bonded to next carbon, means it will get second priority, and CH3 will get third priority. Now draw an imaginary arrow from first priority to second priority. So here we can draw arrow in the right direction. So the configuration of this molecule will be R. Now again, oxygen has highest atomic number, so it will get first priority. Hydrogen will get fourth priority. CH3 will get third priority and C6H13 will get second priority. Now when you draw an imaginary arrow, it will go in the other direction. So the configuration of molecule will be S. Now let's read from the book. Thus SN2 reaction of optically active halides are accompanied by the inversion of configuration. So here as the configuration changes from R to S. So this is inversion of configuration. In case of optically active alkyl halide, SN1 reactions are accompanied by the racemization. Can you think of the reason why it happens? Actually, carbocation formed in the slow step being sp2 hybridized and it is planar archival. The attack of nucleophile may be accomplished from either side of plain carbocation, resulting in the mixture of the product, one having the same configuration, means OH attached to the same side as halide ion, and the other having the opposite configuration, in which OH attached to the opposite side of halide ion. So here when you see, this is the carbocation and this carbocation is planar. This is the planar structure. OH may attack from the front side or it may attack from the rear side. So as a result of it, either it will get attached to the same side where Br is attached. Here Br is attached on the right side of the carbon. If it get attached to the same side, or in the other case it may get attached on the other side. So if it get attached on the same side, you will get retention of configuration, or if it get attached on the other side, you will get inversion of configuration. And if you get both the structures in 50-50, you will get the racemic mixture. That's how acid-1 reactions are accompanied by the racemization because of the formation of carbocation, which is a planar structure. A nucleophile may get attached on the either side of the carbon atom. In the next video, we will learn about the elimination reactions.